My name is Todd Coleman. Today we're going to discuss how we cut our database costs and cloud dependencies fast. I'm the technical co-founder and chief architect at Yieldmo. I've spent most of my 20-plus year career in ad tech specializing in high-frequency, low-latency systems. So today we're going to discuss Yieldmo's journey from DynamoDB to ScyllaDB. We'll cover our database requirements, the options we considered, why we chose ScyllaDB, how we managed the migration, and the results. Let's start with a brief introduction as to who we are. Yieldmo is an online advertising platform that helps brands create engaging ad experiences, optimize their ad spend, and reach their audience through machine learning. Simply put, we provide the technology for online publishers, websites, and mobile apps to place ads. We connect publishers and advertisers in real time as the page loads using an auction-based system, while also optimizing the look and feel of the ads through AI. We've spent years developing and refining machine learning techniques to help us choose the best ad for a given situation. Our ad platform depends on ultra-fast, high-throughput database lookups at scale. Nearly every ad request triggers a database query, retrieving crucial machine learning insights and device identity information. These queries enable our ad servers to conduct effective auctions and provide our advertising partners with the data that they need to decide whether or not to bid. Additionally, they help us track which ads we've already displayed to a particular device, allowing advertisers to manage frequency caps and optimize ad delivery. When a user visits a website, an ad request is sent to us. We analyze the requests, solicit potential ads from our partners, and conduct an online auction to determine the winning bid. The database lookup, delivering identity information and machine learning insights, must happen before any of those calls to our partners. The entire process of delivering an ad generally occurs within 200 to 300 milliseconds, most of which is used by our partners to evaluate and place bids. To maximize their decision-making time, our database lookups must occur in single-digit milliseconds. With billions of these transactions happening daily, our database must be fast, scalable, and reliable. If it goes down, our ad serving system infrastructure ceases to function properly. Simply put, it is mission critical. Since our production infrastructure runs in AWS, we historically relied on DynamoDB. It was reliable and easy to use, which we appreciated, but it had some drawbacks. Before discussing those issues, let's outline our key database requirements. Our workloads are extremely read-heavy, with several hundred queries per second. As we continue to scale, maintaining low latency is essential for sustaining auction performance. Our write operations fall into two categories: a continuous stream of real-time data from our partners, essential for matching our data with theirs, and batch updates driven by machine learning insights derived from our historical data. This balance of high-frequency reads and structured writes demands a database that can handle large-scale, low-latency access, also while efficiently managing current updates without degradation in performance. As our business scaled, our DynamoDB costs increased significantly. However, the bigger issue was that DynamoDB limited where we could deploy our ad serving infrastructure. We primarily operate in AWS, but we also wanted the flexibility to experiment with running ad servers on other cloud providers, such as GCP. In some regions, like in the US East Coast and Northern Virginia, AWS and GCP data centers are close enough that latency is minimal. Hitting our DynamoDB database from any ad server running in GCP there isn't a problem. However, when we attempted to launch a GCP-based ad serving cluster in Amsterdam while accessing DynamoDB in Dublin, the latency was far too high. We quickly realized that if we wanted true multi-cloud flexibility, we needed a database that could be deployed anywhere. So we started looking for alternatives. Let's briefly discuss some of the options we considered. In addition to cross-cloud compatibility, we also aim to reduce costs while maintaining speed, scalability, and reliability. These were non-negotiable criteria for us. Our simplest option would have been to stay with DynamoDB and add a caching layer. However, we quickly determined that caching couldn't fully compensate for geographic latency. Cache misses would be even slower, making this approach impractical. Next, we considered Aerospike, as we had some experience using their database in the past. Aerospike offered the speed, reliability, and cross-cloud support we needed. However, Aerospike gets its improved speed by keeping indexes to the data in memory. Given that our data consists of a very large number of small objects, the memory requirements to index all of them would have been very high. We would have needed an impractically large Aerospike cluster, increasing costs rather than reducing them. Additionally, migrating to Aerospike would have required extensive code changes across several systems, adding weeks of development time. Neither of these solutions met all of our goals. Then we discovered ScyllaDB. ScyllaDB supported cross-cloud deployments, required a manageable number of servers, and offered competitive costs. Best of all, its API was DynamoDB-compatible, meaning we could migrate with minimal code changes. In fact, a single engineer implemented the necessary modifications just within a few days. Now, let's talk about the migration process. We started, of course, with a proof of concept, working closely with ScyllaDB's engineers to develop a migration plan. We initially moved a subset of our ad servers in a single region to ScyllaDB for testing. However, migrating a database of our size while keeping it up to date required careful planning. We needed a way to migrate multiple terabytes of data while ensuring real-time updates remained in sync between DynamoDB and ScyllaDB. Without identical data in both databases, our performance comparisons wouldn't be valid. To migrate the existing data, Scylla provided a specialized migration tool that used a Spark cluster running an RVPC. The migration would take several hours due to the data volume, which led to a challenge handling ongoing writes. Our writes came from two sources: batch jobs, which we could temporarily pause, and a continuous stream of identity data from our DSPs, which we could not pause, as our production system required recent data to be optimally effective. Fortunately, our architecture leveraged Kafka message queues. The identity information enters our system and is immediately written to a Kafka cluster. The secondary process then reads from the cluster and writes to our database. That is so that in the event of a failure, we can replay up to the last several days worth of data. We started by taking a snapshot of the Kafka offsets before starting the migration job, and then setting the migration tool to only migrate the rows last modified before that point in time. Once the migration job on the Spark cluster finished copying the historic data, we created a secondary permanent process to read from Kafka and write to ScyllaDB, starting from the offset snapshot. We started our first POC with ScyllaDB in February 2024. This initial test focused on a single DynamoDB table, consisting of about 28 billion objects and occupying approximately 3.3 terabytes of storage. Using a Spark cluster, we migrated the data to ScyllaDB's test nodes in their VPC, a process that took about 10 hours. After completing the data migration, we resumed processing the Kafka queue from where the snapshot left off, ran a compaction, and verified that our TTLs were set properly. This first POC provided invaluable insights. One unexpected challenge we encountered was that all of our requests were initially directed to a single ScyllaDB node, as there was no built-in mechanism at the time to automatically load balance across nodes. We considered putting the nodes behind an AWS Elastic Load Balancer, but this would have been a substantial cost. Instead, as a temporary solution, we placed all of our IPs behind a DNS-A record and relied on DNS round robin to distribute the traffic. While this workaround sufficed in the initial POC, it was not a viable long-term strategy, as the DNS-based load balancing could result in hotspotting in backend nodes. We didn't find this to be a huge issue during the POC, but we wanted a better solution if we were to move forward. Fortunately, Scylla was already working on one, code that could automatically track active nodes and distribute the load accordingly. However, this required additional deployment work on our side to integrate it properly, meaning that ScyllaDB wouldn't be an exact drop-in replacement for DynamoDB, but once the Scylla engineers delivered the new functionality, we found that implementing it was a simple matter. The second POC was significantly more complex. This time, we aim to migrate all of our data across all 5 AWS regions. We had already successfully evaluated ScyllaDB's performance during the initial test, but we decided that a second POC was necessary for validating the newly implemented load distribution mechanism. Given the high costs associated with reading all of our data out of the DynamoDB database as we migrated it over to ScyllaDB, we plan to roll the POC directly into our production implementation if this POC were to prove successful. The full data migration took about 2 weeks. Managing concurrent data loads across multiple regions was a challenge, but through our close collaboration, Scylla and Yieldmo's engineering teams were able to perform the process with minimal issues. One key finding during this phase was that the i3en EC2 instance types, which we initially hoped to use to reduce costs, did not deliver the required performance. We ultimately determined that we needed to standardize on the i4i EC2 instance type family across all regions to maintain the necessary low latency performance. Another crucial lesson was the importance of carefully managing TTLs and data size. Unlike DynamoDB, where scaling storage is more flexible, ScyllaDB requires scaling in groups of 3 nodes at a time, making incremental scaling less straightforward. It takes some time and planning to scale out, so it's important to carefully plan for your ultimate data storage needs and to set up proper TTLs to keep track of your data growth. After evaluating the cluster performance across all regions, we were very happy with the POC results, and we moved to ScyllaDB as our primary database. We had been maintaining our rights to DynamoDB as a backup, but in time we gained enough confidence with ScyllaDB's reliability and performance to eventually turn off the rights to DynamoDB in most regions. Today, we're still fully running in AWS, but we now have the flexibility to experiment with other cloud providers. Our nodes make good use of Amazon's i4i instance family, as they're optimized for high performance access to their local SSDs, instead of most instance types which require network attached EBS drives. We like to keep our data storage at about 50% of available disk space. Reaching 70% data storage will trigger us to scale out the cluster. The main cost driver is, of course, the number of servers we run in each region, and that number is determined by the amount of data storage necessary. So we keep a close eye on our TTLs and our data retention policies. Let's finish by looking at the impact of our migration. The biggest benefit that we've unlocked is multi-cloud flexibility. However, even if that wasn't the goal, our migration would have been worth doing. Our database costs were cut in half from what we were spending even with DynamoDB's reserved capacity pricing. As a bonus, we also saw modest improvements in database latency. One of our initial concerns was moving away from DynamoDB's proven reliability. However, ScyllaDB has been an excellent partner. Their team provides monitoring of our clusters, alerts us to potential issues, and advises us when scaling is needed. In terms of ongoing maintenance overhead, the experience has been more or less comparable to DynamoDB's, but with greater independence and substantial cost savings. This concludes our look into Yieldmo's migration journey. I hope you found it insightful. My name is Todd Coleman. Feel free to reach out if you have any questions.